All right. So going into today, um, looking at today's work, we are continuing on with the heat calculations. So yesterday we ended up with temperature conversions. Today we're going to move into calculating specific heat. So we're going to get this formula, Q equals MC delta T. I'm going to identify what the components are. This is one of the few formulas we actually get. The rest are going to be like more dimensional analysis that we have to kind of figure out where we're coming from and going to. Um, so, so looking at this, I do want you to know for temperature change, the Fahrenheit, if you're given information in Fahrenheit and you need to know Celsius, that formula is in your periodic table reference packet, as well as the Celsius to Kelvin conversion. Um, the one that's not going to be there is if you're given the information in Celsius and it's asked for Fahrenheit, or if it's given to you in Kelvin, like number one, and asked for Fahrenheit. You're going to have to kind of manipulate the equations to get there. So looking at number one for this, the first step that I would have done is I would have went Kelvin to degrees Celsius, and then from degrees Celsius, I'm going to go to Fahrenheit. So my first step is I had 310 Kelvin, and so I'm going to subtract 273.15. And I'm not really going to pay a whole lot of attention to the 0.15. I'm going to keep it in there, but I'm recognizing that this original temperature was measured to the ones place in scale. I'm going to treat that 0 as a real number this time, or as a significant number this time, because that's just kind of how I'm perceiving that temperature scale to have been read. All right. Sig figs are kind of weird on temperatures. Basically, my answer is going to be to the ones place on this one because of the information given. All right. So I go here. Now, I don't want to round in between, but I get 36.85 degrees Celsius that I'm going to use in my conversion. So 310 minus 273, unless I did math wrong. All right, now I'm trying to solve for Fahrenheit. So in the packet yesterday, I gave you that degrees Celsius equals Fahrenheit minus 32 divided by 1.8. If we manipulate the equation to solve for Fahrenheit, it's going to be degrees Celsius, which is 36.85 times 1.8 plus 32. So I end up with, when I put it to the ones place, I ended up with 98 degrees. All right, questions? All right, so for this one, we're just going to use this formula, plug it in there. So degrees Celsius equals 55 minus 32 divided by 1.8. And I'm going to keep it in a whole number again. So 13 degrees Celsius. And then converting Celsius to Kelvin. So Kelvin equals negative 25 plus 273.15. So again, keeping it to the whole number, I end up with 248. Questions on that? All right. So again, yes. No. So for Kelvin, Kelvin is reported in unit Kelvin. They don't show a degree symbol for it. But Celsius and Fahrenheit both have a degree symbol. Now, if you are typing this into a question on a test, if it's an open-ended question where you have to type in your response, you won't have to do the degree at all, either one. You don't show, on the Southeastern test, they don't make you put the units in. You just put the number in. Yeah. All right. So today there's not a lot. It's really just learning how to use this one formula. I am going to give us a couple of definitions to begin with, and then we'll jump right into looking at information that we're given and then using it to solve problems. So, to start off, we're going to be dealing with a term today called heat capacity or specific heat capacity. So heat capacity is the quantity of heat, and it's typically measured in joules, but the quantity of heat required to change the temperature of a given amount of substance by 1 degree Celsius. All right, so it's how much heat does it take to change a certain amount of material by 1 degree Celsius. That is not the right. That's not the right one. I need to use one of these. All right. Now, so right now that's probably not going to mean a lot. But so if I have 1 gram of copper, I want to know my heat capacity is basically telling me how quickly or how slowly that copper is going to heat up if I add it to a heat source. All right. So metals are going to have typically a typically lower heat capacity because they heat up pretty quick. Whereas something that has a high heat capacity, it's going to take a long time for it to heat and change, things like that. So and then at the same note, something that has a high heat capacity, once it's warm, it'll take a long time to cool off. So that's kind of what heat capacity says. All right. When we express this amount in grams, we actually, instead of just calling it heat capacity, we call it specific heat capacity. So in this class, and if you have your periodic table reference packet, or if you have one, if you don't have one, I always have extra copies up there. But on that second page of it, there is actually a table that lists specific heat capacity that we'll be using on tests and things like that. But the unit that it's going to use to express specific heat, in the equation that we're using today, the specific heat is represented by that capital C. So that is all right. That's specific heat. The units is going to be joules per gram degrees Celsius. So notice the units has joules in it, grams in it, and degrees Celsius. So it's kind of like a conversion factor in and of itself. All right. And so we can use that to cancel units to solve for one thing or another in our equation. All right. So, does everybody have what they need off of this? Okay, I'll wait. Not sure why. All right. So, the one that this is the one out of our textbook, the table that goes for this out of our textbook. Like I said, in the reference packet we have it. It's right here in this top left corner. And so that table has certain things listed like aluminum, copper, ethanol, gold, iron, lead, platinum, and so on. But it has the density listed for it and has specific heat capacity. Both of those are like constants for a type of material. All right. So notice on here, so when we compare water to everything else, what do you notice about water's heat capacity compared to everything else on that list? It's higher. Now think about putting a pot of water on the stove to boil. Does the water heat up immediately or does it take a long time? It takes a long time. So that heat capacity is kind of what's determined that. So since water is so high, it takes a long time. You set a spoon on the stove and you set it on the burner and you don't realize it's on the burner and you go to grab that handle, it's hot. All right. All right. So the metal, let's just say the spoon's made out of aluminum or silver. All right. Both of those are fairly low compared to water. They're going to heat up much faster. All right. Now, the same thing happens in the reverse. That piece of metal, once it's taken off the heat source, it cools off pretty quickly. Once the water's taken off the heat source, that water can stay hot for a very long time. So think about like I pretty much only take showers. I don't like sitting down in a tub, but if you ever were to sit in a tub and you run that hot water in there, think about how long the water stays warm. All right. And that's kind of what we're looking at for that. Now, I will tell you another substance that has a fairly high heat capacity is glass. Glassware tends to hold its heat for a pretty good while. And one of the bad things about glass is hot glass looks just like cold glass. Like there's no way to look at it and say, oh yeah, that piece of glass is hot. And so like we're working in the lab and we look at it and we think, oh yeah, it's been off the hot heat for long enough, and you go to grab it and you still burn your fingers on it. I can't tell you how many times I've grabbed a piece of hot glass and not thinking. Even like in the oven, to pulling something out the oven, you're cooking in that Corningware baking pan or whatever it is, Pyrex baking pan, and you grab it and you don't even think about it being hot. All right, so I gave you the table again. If you want to heat up a metal plate to as high of a temperature as possible for a given energy input, what metal should we use if we assume that they all have the same mass? So which one would we say is probably going to heat up the fastest and get the hottest? Lead and gold. All right. And think about lead and gold. What do you know about their melting points? They're pretty low. All right. Comparatively speaking, taking lead and gold, comparing it to like aluminum or iron, you need more heat to do those up. They both will melt at relatively easy melting points, but gold is super, super soft when it's pure gold. And I mean, gold's melting point is almost not much higher than room temperature. Yeah. Well, I mean, aluminum's got a 0.9, so it'll get hot, but it takes a little while. I think part of the reason why aluminum foil doesn't get as hot is its reflective quality. So it's actually reflecting the heat off and not absorbing it. If you flip it over to the duller side, it might get hotter. All right. Let's look at where we're at. All right. So, because we like to quantify everything, because we want to put numbers to everything, we have an equation that we can work with for this. So, like I said, the way that we're going to measure energy in this class is looking at heat. The only measurement that we can actually take in this class as far as energy is temperature change. We can measure the temperature stuff. We can stick a thermometer in it and watch what happens to the temperature. All right, that's an easy part. But I want to relate that degrees Celsius, degrees or unit Kelvin, degrees Fahrenheit. I want to relate that to a number in energy. So heat here, which is represented by the letter Q, is our thermal energy. All right, that's our thermal energy. Mass, so Q is going to be measured in joules. What other unit did I say yesterday that we can measure heat in? Calories. So that Q will only ever be reported to you in joules or calories. All right. The M represents mass. We are typically, for this calculation, we're going to measure mass in grams. Sometimes it'll be in kilograms, things like that, but we're going to have to convert it to grams because our unit for C here for specific heat. So the reason why this mass has to be in grams is because this unit is in grams. All right. So we have to keep those in the same units. All right. And then delta T just means change in temperature. All right. Our temperature change. So for this one, delta T is actually your final temperature minus your initial temperature. So your ending temperature minus your starting temperature. All right. Now, so the kind of catch thing that can happen here, our heat energy in this class, when we deal with negative numbers, we're not actually saying it's minus that. What we're really saying is that the direction, we're talking about the direction of flow. So one of the things that is going to be important to recognize is that our Q here can be positive or negative. So Q can be a positive number or a negative number. So remember yesterday we talked about endothermic versus exothermic. What did we say is happening to the heat in exothermic? Where is it going? It's going out of the system. So what that means in terms of Q in an exothermic system, helps if I write a Q. Q is going to be negative. It's going to be a negative number if the heat is leaving the system. What that means is your initial temperature is larger than your final temperature. That's how we end up with the negative Q. All right. Endothermic heat is entering the system, so it gives us a positive Q. It's not, for the most part, just pay attention to if I'm not always going to care if you know it's endothermic or exothermic. What I am going to care about is if your initial temperature, your starting temperature is bigger than your final temperature, you should have a negative answer. If your final temperature is larger than your initial, you'll have a positive overall answer. So you can have a negative number as an answer for Q. Now, most of the ones that we do, we are going to look at temperature change in water. So we're not going to really see that. So if we're using calorimetry, we're going to be using water. Or other times we'll be just looking at the object itself. All right. So let's look at a problem and see how we use this. All right. So example problem for this would be, gallium, and I'm going to talk about gallium first. Gallium is a pretty cool metal. All right. If you look on the periodic table, actually mine doesn't show this, but gallium's melting point is Ga. It's number 31 on the periodic table. Its melting point is just about body temperature. All right. So if I take a piece of gallium, a hunk of gallium, and set it in my hand, it's going to go from a solid to a liquid. All right. So it's really cool. If you've ever seen liquid mercury, liquid gallium and liquid mercury look very, very similar. All right. It's a liquid metal. It just shiny. It looks cool. All right. Gallium's not as dangerous for our bodies as mercury is, but that's just something you need to know about gallium. So the question says, how much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 degrees Celsius to 29.9 degrees Celsius? All right. And then they also tell us that the specific heat of gallium is 0.372. So, we don't have that one listed on our chart in our periodic table. So that's one. Most of the time, the homework questions will give you the specific heat unless it's asking you to solve for that. So let's look at what information we have and all of that. So specifically, what is this question asking us to solve for? Well, we're going to have to get, this would represent our TI. This would represent our TF. So we can get, if we do TI minus TF, we can get delta T very easily. The thing is it's asking for how much heat. So what symbol is going to represent heat? Q. All right. So we're solving for Q. All right. So just kind of going through and looking at my information. 2.5 grams, what is that? That's a mass, right? We already talked about, we have our TI, TF, that's our delta T. All right. And then this represents specific heat. Okay. So we have our C, our M, and our delta T. So we have all the information in this. That means we can solve for Q by just multiplying them together. So pulling them up, and I didn't solve it out, but if I wanted to set up to solve for delta T, I have my TF, which is 29.9 degrees Celsius minus 25. So, but just going ahead and starting to put information in there. So if I put my M in there, that's my 2.5 grams, right? I drop my C in there, that's 0.372 joules per gram degree Celsius. Notice that I'm multiplying grams here by grams in the denominator, so that canceled out my grams. All right. And then 29.9 minus 25.0. All right. Now, delta T will affect sig figs. Notice both of those are going to the tenths place. So when we do that calculation, I get 4.9 degrees Celsius. All right. So I have a number that my mass is 2 sig figs, my specific heat is 3 sig figs, my temperature is 2 sig figs. That means my answer has to be in 2 sig figs. Now, when I put my temperature change in there, that got rid of my degrees Celsius. So the only thing I'm left with is Q, or the only thing I'm left with is, and that shouldn't be a 1, that should be a joule. Sorry, I'm not sure why it showed up as a 1. So that the only thing left over is my joules, and all I have to do is multiply 2.5 times 3.72, 0.372 times 4.9, and when we do that, I get 4.557. I need that in 2 sig figs, so what's my answer going to be? 4.6. All right, this one is pretty easy as far as plugging it in. You just have to recognize that grams is always going to be your mass. Temperatures, you have to figure, the hardest part is figuring out which one's your initial, which one's your final. And that's just going to be pay attention. So it says, it might say your final temperature was, or it might say you raised the temperature to. Sometimes it'll just tell you that the temperature changed by this amount, and then you didn't even have to do final minus initial, it just gave you the delta T. So I actually, specific heat problems I like because they are formula based, and it's just kind of plug the number in and change it as you need it. All right. Don't get full, or don't get lulled into the thing to think that you're always just solving for Q. All right. Sometimes it'll ask you to solve for mass. Sometimes it'll ask you to solve for delta T. Sometimes it'll ask you to solve for C. But they're always going to give you three pieces of numeric information and one unknown. All right. So let's look at another one. I'm going to give you an opportunity to kind of work this one out on your own. But it says a chemistry student finds a shiny rock that she suspects is gold. She weighs the rock on a balance and determines that its mass is 14.3 grams. She finds that the temperature of the rock rises from 25 degrees Celsius to 52 degrees Celsius upon the absorption of 174 joules of heat. It wants us to find the heat capacity. Therefore, using the heat capacity, we can find out what that rock is made out of. So, first thing I'm going to look at is, question is asking me to find heat capacity. So I have Q equals MC delta T. How can I manipulate this equation to solve for heat capacity? What do I need to get by itself? have to get the C by itself. So C is Q over M delta T, because all I have to do is divide the M delta T on both sides to get rid of it. All right. So that should lead you into where to go from there. Now all you have to do is plug the numbers in and get them. So take a minute, try to solve this one, and we'll come back and figure out what element this is. Yes. So that's going to be it. Yeah. Because so remember, experimental data is not always going to be perfect. So that number that you're seeing on the table is like an average of doing it 10,000 times. All right. And they also did it, they also calculated it to a greater precision than we're calculating. So that could make a difference too. All right. So looking at this, I have I got my equation. I know what I'm solving for. I'm solving for C. That's my specific heat. So now I can start using the information in my problem. So I know that my mass is 14.3 grams. The reason why I know that that's mass is because it's grams. I know that my Q is 174 joules because joules represents heat. All right. My delta T is going to be my final temperature, which is 52, minus my initial temperature, 25. And so that's degrees Celsius. So my temperature change is 27 degrees Celsius. All right. So plugging it in there, 174 joules over 14.3 grams times 27 degrees Celsius. Notice that none of the units cancel each other. So that means that our answer has to be in joules per gram degree Celsius this time. So we're making a compound unit. And when we do that, we're solving to 2 sig figs because 27 degrees is our smallest amount. So 0.45 is what I get. And so I take that 0.45 and I look at my list. The closest thing to 0.45 is iron. So my assumption is this is not gold. It is iron. More than likely, if she's thinking it's gold because of appearance, there's something called fool's gold, which is iron pyrite. But it's primarily iron with some other minerals in it that make it have a gold shiny appearance. All right. So questions about this? So oddly enough, that is it for the notes. All right. So talking about my quiz that I'm planning for tomorrow. The quiz that I'm planning for tomorrow is going to be covering mostly Chapter 1 and Chapter 2. There will be a few questions from Chapter 3. The majority of the questions that I'll pull from Chapter 3 are identifying things like pure versus mixture, element and compound versus homogeneous, heterogeneous. I will probably put 1 or 2 temperature conversions on there. All right. I have the way I have it set up right now, I think we're going to do it through Quiz. That's what my plan is. And so in Quiz, I have a question bank of about 30 questions. I'm only going to assign 15. So not everybody's going to get the same questions. You might get a bulk of questions that is more heavy to one chapter than another. I can't control how it does. It just pulls from my bank. I try to put about an equal number of everything so that it balances, but the computer's going to do what the computer's going to do. All right. But to kind of help you prepare for this, if you go into Moodle, and I'm going to show you how to do this real quick. Let me stop something real quick.